Welcome to Pavinar's, webinars for the pavement community. My name is Andrew Bram, and today we'll be talking about viscoelasticity and asphalt materials. We're going to start with some basics, and that includes elastic behavior, elastic plastic behavior, and viscous behavior. We're then going to transition into spring behavior and dashpot behavior, which are mechanical analogues, and we'll combine various springs and dashpots to explore linear viscoelastic behavior. In order to characterize viscoelastic materials, there's various models we can use, including the power law, the sharp and parabolic model, the Viscoelasticity, 2S2P1D, and SVCD. And then for material behavior, we're going to talk about relaxation and creep compliance, the convolution interval and correspondence principle, and time temperature superposition. Now, this topic can easily be a 2 to 3 day workshop, and this will be a long Pavinar. Usually these are about 30 to 40 minutes. I anticipate this one being 50 to 60 minutes, but I'm only going to scratch the surface, so I will provide some additional materials at the end, but I'm just going to cover the basics in this Pavinar. Now, I do also want to recognize who has helped me obtain this information, and that includes Dr. Richard Shapery at the University of Texas, Austin, Dr. Richard Kim at North Carolina State University, specifically the workshop he puts on, which is titled Viscoelastic Continuum Damage Model of Asphalt Mixture and Its Applications. And I was fortunate enough to attend this workshop in July 2024. My good friend and colleague, Dr. Ishan Dawe at the University of New Hampshire. Back when he and I were in graduate school, he wrote a short course called Introduction to Viscoelasticity in June 2006, and I used notes from that as well. And then finally, my friend and colleague, Dr. Shane Underwood, also at North Carolina State University, who has provided me with free consulting over the years whenever I have questions about all things viscoelasticity. And I'm just trying to stay afloat. I don't pretend that viscoelasticity is a core research area of mine, but I do think it's very important to understand, and I hope that this Pavinar provides at least a brief overview of the highlights. So let's start with elasticity. What is elasticity? Well, in order to show what elasticity is, let's look at a cylindrical rod that has an initial cross-section area A0 and an initial length of L0. Then let's apply a force, and we get a small elongation. So we get a delta L, which is L minus L0, and the force we applied is K times delta L. And that K is a function of material and geometry, and specifically the modulus of elasticity. And so we can substitute into K E times A0, so we have the force equaling E, the modulus of elasticity, times A0 times delta L over L0. And we can rearrange that equation. We can take the area over to the left side, and then you can clearly see where the stress equals E times the strain, where sigma equals E times epsilon. So this is a fundamental elasticity theory. Now we can also take a look at it in graphs. A linear elastic material is where you load something with some sort of stress. You measure the strain. When you unload it, it returns on the same path in a linear fashion. So you can just go back and forth, up and down. That's a linear elastic material. You have nonlinear elastic materials where, again, you apply some sort of stress and you measure a strain. It tracks on the same path going up and down, but it's not a straight line. So it's a nonlinear elastic material. And then we have a concept called inelastic or hysteresis. I apologize. And that's where you load it on one path, it unloads on the other path. But the most important thing to notice here, in elasticity, the strain always returns to zero. Any sort of deformation that you put on the sample goes back after you've taken the load off. So all of the strains start at zero, and they all return to zero at the end. Now, when we incorporate plasticity into this, this means we apply some sort of strain, but then it does not return to zero. So you have a perfectly plastic material where it returns back to a stress of zero along the same slope as the loading that was applied, Or you have something called strain hardening, where there's some sort of kink in that loading cycle, but then again, you return back at the same slope, but there is some sort of permanent strain. And so here with an elastic plastic material, you introduce some deformation, and that deformation is irreversible. Now with viscosity, the easiest way that I have found to qualify viscosity is to pretend you have two parallel plates, and between those two parallel plates you have a purely viscous fluid. And the parallel plates have an area of small a, and what you do is you apply a force, and you want that force to be applied so the top plate moves at a constant velocity. And that velocity can be represented here, and the velocity is 0 at the bottom, and it is at the maximum at the top, and you can see this is a linear relationship in this viscous fluid. And what you can do is there is a coefficient of shear viscosity, which is eta, and the force equals eta times A times the change in velocity over the change in height. So that's a fundamental principle correlating the deformation to the force. And the strain rate is epsilon dot, and epsilon is d epsilon over dt. Epsilon dot is d epsilon over dt, which is equal to dv over dy. So you can replace that into our equation and divide by a. So F divided by a equals eta times dv over dy. And then substituting in that epsilon dot, you get the stress equals the coefficient of shear viscosity times epsilon dot. And so this is how we get the equations behind viscosity. Now let's try and take a look at that in graphical form. So pretend you have 4 different input strains, and those input strains are E1 through, or epsilon 1 through epsilon 4, epsilon dot 1 through epsilon dot 4. And from those 4 strains, you get 4 different stresses. So you have an input strain and an output stress. And what you can do is you can cross plot the stress and the strain. So now we have stress on the y-axis and strain on the x-axis. And you can see the 4 levels of stress corresponding to the 4 levels of strain. And then you can plot that by the stress strain rate, which is the stress by epsilon dot, which is the strain rate on the x-axis. And you can see this happens to be a non-linear example. So as the stress increases, the change in stress decreases, so it's nonlinear. But then there is a special situation where if you have a linear relationship here, so therefore if your eta is constant, this is a special situation, and this is what we call Newtonian behavior. So that is the basics of elasticity, elastic plastic behavior, and viscosity. So let's start taking a look at the mechanical analogues. So we're going to be looking at creep versus relaxation and springs and dashpots, and then going into linear viscoelasticity. Now we're already 8 minutes in, and we're less than a fourth of the way through, so I'm going to take a little bit of a break. And I love airplanes, and on the top there is a picture I took of my China Eastern Airbus 340-600 landing at LAX. And on bottom was a Qantas A330-300 in Brisbane that I was able to take. I absolutely love airplanes, and I love showing pictures of them. So those are 2 planes that I've been on. Now back to the mechanical analogues, let's talk about creep versus relaxation, and we'll go into springs and dashpots and finish up with linear viscoelasticity. So when we think about a creep test, you have a constant stress, and you measure the strain. And this is called stress control. So over time, you simply apply some sort of constant stress, and you see what happens to your material. And in the world of viscoelasticity, we often relate this with the term creep compliance. And creep compliance is simply the change in strain over time divided by that initial stress. So you apply some sort of initial stress at that time of application, your strain starts increasing, and you can see it's asymptotical. So it gets to some sort of maximum, well, it never gets to some sort of maximum limit or maximum value. It's asymptotical, so it approaches a maximum value. So this is the creep test. Constant stress, measure strain. The relaxation test, on the other hand, is a constant strain, and you measure the stress. So this is called strain control. So you have your sample, and at some point you apply a constant strain, and then you measure the stress. And this is related to relaxation compliance, or E of T. And E of T is the stress over time divided by that initial strain. And you can see what happens is when you apply that strain, there's a jump in stress. And then as you continue applying that strain at a constant rate, the stress relaxes. Hence why it's called a relaxation compliance. Now, if you know about viscoelasticity, you also know that it's often represented with mechanical analogues. So let's start looking at these concepts through the lens of mechanical analogues. So starting with the spring, if we have a single spring, it has some sort of elastic modulus, and that elastic modulus can be either in pounds per square inch or newtons per square meter. And in creep and recovery tests, you apply some sort of constant stress, and then you take that stress off. And you measure the resulting strain, and when you take that stress off, the strain returns back to zero. So when you have a spring, the two curves look the same when we're talking about the creep and recovery. Now for the relaxation, it's a little different. You apply some sort of constant strain, and the stress, resulting stress, is also a constant. So you can see here a fundamental difference between creep and recovery. With the creep, you apply a stress, you measure the strain. When the stress is released, the strain goes to zero. But in relaxation, when you apply a strain, that constant strain results in a constant stress being recorded. So this is a spring mechanical analog. The next most common is a dashpot mechanical analog, and this measures the viscosity of a material. And this is represented by eta, and eta is the coefficient of viscosity, and that's either measured in poise or Pascal seconds. So again, let's pretend we do a creep and recovery test. You put some sort of constant stress on, and you apply that for a certain amount of time, and then you release it back to zero. Well, the strain looks a little different. You can see that the increase in strain is simply that applied stress divided by eta, but then when you remove the stress, the strain stays on, so it does not decrease again. And with relaxation, you apply some sort of constant strain at some time, and it's a very interesting response. Essentially what happens is the stress goes to infinity immediately, but then immediately then drops down to zero. So you've essentially maxed out that dashpot by putting the maximum stress on, and then it doesn't matter how much more strain you put on there, your stress will be zero. Now it's not very convenient to have just a single spring or dashpot, so we also put these together. So for linear viscoelastic behavior, we have what's called the Maxwell model. And this is where you have one spring and one dashpot in series. And you either apply some sort of stress or some sort of strain. So when we're looking at the creep and recovery, you apply some sort of stress, and then at T1, you remove that stress. And you can see here, the second you apply that stress, a deformation occurs, and that is the stress divided by the modulus of elasticity. Then you have a slope increasing at the 1 over eta, and then when you remove that stress, it drops by that initial stress divided by the modulus of elasticity, but then it remains constant at T1 divided by eta times that initial stress. And so you can see the strain over time can be measured by the addition of those two components. Relaxation is obviously a little bit different. You apply some sort of constant strain. You have a jump up in stress, and that jump up is the modulus of elasticity times the initial strain, and then it decays over time. And you can see the equation on how it decays. It decays at the rate of eta times the strain rate times 1 minus e to the negative et divided by eta. So we now have our both visual and mathematical models for the Maxwell model. Now, the Maxwell model is a linear viscoelastic combination, and this is where the spring and the dashpot are in series. We can also show them in parallel, and that's called the Voigt model. And here again, you have some sort of elastic modulus and viscous dashpot, and you apply a stress or a strain to this model. Let's just assume we put some sort of constant stress on the sample until T1, then remove that stress. And you can see here there are two distinct different portions of this curve. Before T1, you can see the relationship of stress and strain. And this looks pretty similar to that Maxwell model before in the relaxation component. But then afterwards, you can see its decaying relationship. And again, the strain is a function of the initial strain at T1, or the strain at T1, the elastic modulus, the change in time, and eta. For the relaxation, you apply a consistent strain. Again, it jumps up immediately, and then it immediately returns down to the modulus elasticity times that initial strain, and then it stays constant as the strain is constant. And we can continue building on this by putting those two models, the Maxwell and the Voigt model, in series. So now we have two springs and two dashpots. We apply our creeping recovery load, and you can see it becomes much more complex. There's some sort of initial displacement, but then the slope of the displacement is a function of not only the initial stress, but also the two modulus elasticities of the two springs. And then the recovery is similar, where you have a portion where it's that one spring releasing the E1, but then there's a decay with the E2, and there's some sort of permanent deformation because of that eta1 dashpot. With relaxation, you have a jump to the initial, or the at the very beginning, it is the first spring's modulus elasticity times the initial strain applied, and then it decays as shown in that curve. Now, for linear viscoelasticity behavior using the Weikert generalized Maxwell, you can see you have several springs and dashpots in parallel, and then one single spring. That one single spring is E sub infinity, and you can see that stands on its own, but then you have a summation of all of those Maxwell models. So the springs and dashpots in series, you have multiple ones in parallels, and you can have as many as you would like. Kelvin generalized Voigt, you flip that on its end, where you have a single spring and then several springs and dashpots in series moving down. And a similar equation, you have your d sub t is 1 over e sub m, the t over eta sub m, and then the series of the additional springs and dashpots in parallel. In series. So linear viscoelasticity in summary, there are literally thousands of combinations of springs and dashpots, both in parallel and series. And this is why the workshop on viscoelasticity could last 2 to 3 days, because there's more that we could talk about. I just wanted to lay down the foundation of different possibilities. And really at the end of the day, when we're looking at these springs and dashpots, the springs offer modulus of elasticity, or E. The dashpots offer the coefficients of shear viscosity, or eta. And we're just trying to put these in series and parallels and trying to represent what the viscoelastic material, and in this case the asphalt mixture, is doing and how it's behaving. The plasticity comes into play when you have a non-reversible change of shape, and so putting it all together, if you apply some sort of stress to your material, this is everything put together. You can see we have strains from the viscoelastic and viscoplastic components. You have plastic strains, you have elastic strains. Those all are summed together to T1. And then at T1, you then have continued viscoelastic strain gain, but you also have a recoverable elastic strain, a recoverable viscoelastic strain, and then some permanent plastic and viscoelastic strain as well. So that graph on the lower right is really what we're doing with asphalt materials, is trying to understand how those responses to stresses applied impact the material. And that graph on the lower right-hand corner is everything put together. All right, moving from mechanical analogues to material characterization, we're going to talk about 6 models. We're going to start with the power laws. We're going to then talk about the sigmoidal model, the sharp model, move into the parabolic model, the Hoyt-Sayre model, and then 2S, 2P, 1D. Before we get into these models, as advertised, got a couple more airplanes for you. On top is a Delta Boeing 767-300 that I flew into Atlanta. And then on bottom, I was very fortunate to be able to fly an A310. Those are very difficult to fly on these days. They're very rare passenger planes. And this is a Korean Air in Seoul that I was able to fly. But moving on, next section will be power laws, the sigmoidal model, the sharp model, parabolic model, Hoyt-Sayre, and 2S, 2P, 1D are the 6 models that we'll talk about. So in order to talk about these models, we're going to talk about the unit response function, or R sub H. And the unit response function can be either creep compliance, D sub T, which again is where you apply a constant stress, or relaxation modulus, E of T, where you apply a constant strain. And something that we use a lot in asphalt materials is the dynamic modulus. And the dynamic modulus is the stress divided by the strain. And you can see there's a phase angle involved as well. And if we look at the dynamic modulus, it's where we apply a sinusoidal load. And you have a constant stress or strain amplitude. And those curves are shifted in some way. So you apply a stress and a strain results, but there's a shift to that, and that shift is the delta T. So this is a very, very common way to analyze asphalt materials, is either with the creep compliance or the relaxation modulus, and by far the most popular is the dynamic modulus, which is E star. So let's start out with some power law models. Let's look at E of T and D of T. If it's a pure power law, it's simply E of T equals E1 T to the negative N. So this is the most simple power law model that you can have. And in this equation, you can replace E with D. They're interchangeable. The same with the generalized power law. This is where you have some sort of initial, relaxation or creep compliance. And again, you can replace D with E, but it's just that pure power law, and you add an initial either creep or relaxation. Then we start getting to the modified power laws, and here we cannot simply replace them one for one, but you can see here we have an initial and then some sort of additional either creep or relaxation, and they're functions of either lambda or the initial modulus. And you can see with the creep, the lambda is in the numerator. In the relaxation, the lambda is in the denominator. So you can see how those flip. And that's the modified power law. With the modified power law series, this just introduces the concept that we have many different either creep or relaxation components, and we have to sum those together from either I to N for creep or I to M for relaxation. And then finally for the Prony series, this is again much more complicated, and you can see here, but again, that there's some sort of initial values and then summations following them. And you can see here for the modified power law series, and the Prony series, E and D are not simply interchangeable. For the pure power law and the generalized power law, they are. But then with these more complicated power law models, you do need to separate them and keep them separated, as essentially the E's, the moduli, and the lambdas flip in the equation. Now, all those values on the far right side are essentially determined by data fitting. And so you collect the raw data, and then you do some sort of either minimizing the sum of the squares or some sort of analysis in order to data fit and put an equation to the data that you had collected. Now, I had mentioned before that dynamic modulus is one of the most popular, and this is a sigmoidal model. And when we're looking at the sigmoidal model, you can see here where you have the log of the dynamic modulus is essentially an equation that's based on 4 fitting constants and a reduced frequency. And this is what's used to build what we call master curves, and I'll talk about that more later. But if you look up AASHTO R84, that is the fundamental standard that we use in order to build our master curves. And again, you can see the log of the dynamic modulus is a value of b plus that maximum dynamic modulus minus b, and divide by 1 plus e to the d plus g log of the reduced frequency. Now, I'm not going to spend a whole lot of time on dynamic modulus, but I do have a Pavinar that was recorded on August 2nd, 2020, and the title is Correlating Field Performance to Laboratory Dynamic Modulus from Indirect Tension and Torsion Bar, and that paper is just as exciting as it sounds, let me tell you. But the Pavinar goes over really how we explored fitting these master curve construction techniques to the data that we collected. So there's a lot more information in there. I just wanted to bring it to your attention that you have a power law sigmoidal model and then a master curve construction sigmoidal model as well in order to get your dynamic modulus. So now looking at the Sharp model, here we have the E of omega, and that is the complex dynamic modulus in pascals. And you can see E of omega is a function of the glassy modulus. So this is the modulus of asphalt materials below the glass transition point. So they're essentially purely elastic. That's a simplified way of explaining that. But you can see we've got our frequency and crossover frequency with the omega, and then you have your rheological index, which is capital R, and that's simply the log of the glassy modulus divided by the complex dynamic modulus that you are collecting. If you're going to use the Sharp model to get this complex dynamic modulus, this is how you calculate the phase angle. So this is how you calculate that offset between the stresses and the strains. And a graph that really helps me here is when we're thinking about the dynamic modulus, or the complex dynamic modulus, E of omega. You can see that E of omega is simply the resulting vector of the elastic portion of your material, which is E prime, and the viscous portion of your material, which is E double prime. So the viscous modulus and the elastic modulus, the resulting vector of those two values of the moduli are your complex dynamic modulus, and then the phase angle is simply the angle of that vector. And so you can imagine you can have similar values of the complex dynamic modulus, but the quantity of the viscous or the impact of the viscous and the elastic modulus can change as that phase angle changes. So I really like that graph because it just breaks down the fundamental relationship between elastic modulus, viscous modulus, and the complex dynamic modulus. Now, if you want a little more reading, there have been several iterations on this Sharp model. It all started with Christian and Anderson back in 1992. Man, back in 1992, I think I was a freshman in high school, which is kind of crazy. But over the years, further AAPT, which stands for the Association of Asphalt Paving Technologists, but further AAPT articles with Maristanu in 1996 and Bahia in 2001 built on the Sharp model. So this is what Christian and Anderson presented in 1992, but this has been modified, enhanced, and changed a little bit with Maristanu and Bahia based on polymer modification and other type of factors. But I did want to just kind of start with the foundational one. And the additional ones are modifications of this, and you're free to look into that more if you'd like. Now, the parabolic model was also actually introduced by Hoyt in 1963, and I apologize if I'm mispronouncing that name, but essentially the strain is nonlinear with time. So you have some sort of function, and that equals A, and that function is the creep function. A is experimentally determined, but you can see that the parabolic portion comes from that T to the K, and T is the time, and then the K value ranges from 0 to 1. And if it is a purely elastic system, or it's a spring, K equals 0. And if it's a purely viscous system, K equals 1. And that means it's a dashpot. And like all good things in the world, no asphalt mixture is either K equals 0 or K equals 1. So it's somewhere in between there. Now this was improved on with the Hoyt-Sea model, which is where you have two springs. You have E naught and the maximum value of E minus E naught. And you can see the E naught is on the left, and then the asymptotical maximum minus the E naught is on the right. But then you also have two parabolic creep elements. You have K and H, and these are called parabolic dashpots. And you can see here in your equation, your E star is the E naught, which is that spring on the left. But then you have the spring in the numerator on the second portion of the equation. But then the K and H are introduced in the denominator. So you can see E infinity is the limit of the elastic modulus. E naught is the elastic modulus. And then you have a dimensionless constant, which is Q. You have the complex number I. You have a frequency, which is represented by omega. And then something called characteristic time, which is tau. And that characteristic time varies with temperature. Now, this was built on, again, by the 2S2P1D model, which was really rolled out by Hervé de Benedetto, but it was built on the Huet-Say model, and you can see everything is the same except that you have an additional dashpot. And that additional dashpot is in the lower right-hand corner of the model, and that value of eta is what causes the 2S2P1D model. And you probably noticed that 2S stands for two springs, the 2P stands for two parabolic elements, and the 1D is one dashpot. And so the denominator is very similar to the Huet-Say model, but then you also have that dashpot in the denominator, and that is the I omega beta tau to the negative 1. But here again we have the E infinity is the limit of the elastic modulus, E naught is the elastic modulus, Q is a dimensionless constant, so all that is the same. I is the complex number, omega is the frequency, tau is the characteristic time, so all of that's the same as the Huet-Say model, but then we also have the eta Newtonian viscosity, which is E infinity minus E naught times beta tau. So that's the addition in the 2S2P1D model. All right, now that we've talked about the material characterization, let's talk about the material behavior. And there's four concepts I want to cover with material behavior. The first is relaxation and creep compliance, which we've talked about already a little bit, but I want to go into a little more detail. The second is the convolution interval, and the convolution integral plays directly into the relaxation and creep compliance. Then we're going to talk about the correspondence principle, which is very, very important. And then one of my favorite parts of asphalt materials, time temperature superposition. I just think that is such a cool impact. Last set of airplane pictures. I was fortunate enough to go to Barrow, Alaska, which has been renamed, and it is now a native Alaskan term, which I cannot pronounce. As you've been listening, you probably know my pronunciation is pretty bad anyway. But when I went there, it was Barrow. That's up on the Arctic Circle, the very northern tip of Alaska. And then also you can see my Turkish Airlines 777W at LAX, Los Angeles, pulling into the gate. But if you like planes, like I do, if you like plane pictures, go to andrewbraham.com/statements, scroll to the bottom, and I've got a whole bunch of picture pages of all the different planes I've been on. I'm a big fan, and actually Dr. Ishan Dawe and I, he introduced me to plane spotting, and we've spent many a good time spotting together. So the last thing we're going to talk about is these material behaviors. Again, there's four concepts: relaxation and creep compliance, convolution intervals, correspondence principle, and time temperature superposition. So for the relaxation modulus, again, this is E of T, a constant strain, and you calculate the stress. And this is the equation you have. So you have your sigma T, and is the integral from 0 to T of E T minus T naught, then delta epsilon T minus T naught over D T naught times D T prime. And all of that equals E of T epsilon naught. And this is where T is the present time and T prime is the historic or previous time. And when we talk about convolution integrals, that is this portion of the relaxation modulus equation. So looking at that integral, that is what we refer to as the convolution interval. Now, why is this important? Well, let's look at an example of a Maxwell model. So if we have a Maxwell model, again, we have a spring and a dashpot in series, and E is the elastic coefficient of the spring, lambda is the viscosity of the dashpot, and tau is lambda divided by E. When we look at this, our equation is E of t equals E times e to the negative t over tau. And so this is an example of how we use the relaxation modulus with one of the more basic models. And you can imagine, just like we had all the different mechanical models, all the different forms of springs and dashpots, you can develop these relaxation modulus equations for any sort of array of spring and dashpots. So it's a very, very powerful tool. I just wanted to show one simple example for demonstration's sake. Now looking at creep compliance, here again you have a constant stress and you calculate the strain. A very similar equation, but it's where the strain is a function of time, and you can see again another convolution interval, but we have creep compliance instead of that relaxation within the integral. So this too is called the convolution integral. So the convolution integral occurs in both relaxation and creep compliance. An example with a Voigt-Kelvin model, here we have a compliance of a spring and a viscosity of a dashpot, and these are in in parallel next to each other. And you can see here the creep compliance is simply the compliance of the spring plus T over lambda, the viscosity of the dashpot. So again, put a whole bunch of these in either a series or parallel, put them all together, and you can represent your asphalt materials. Now, we've been talking a lot about viscoelastic solutions, but let's talk about the correspondence principle, because at the end of the day, viscoelastic solutions are difficult. So it's beneficial to solve for elastic solutions and then transfer them to a viscoelastic solution. And why? It's because elastic solutions are easier, and I don't know about you, but I prefer easy. Viscoelasticity is hard. So is there a way that we can use elastic solutions in order to solve viscoelastic problems? Yes, there is, and that is called the correspondence principle. Well, how do we do that? We use the Laplace transform. And for any function, so any time-dependent function, this is your Laplace transform. So you put it from 0 to infinity, you take the integral from 0 to infinity of that function, e to the negative st dt, and then you get your Laplace transform, your f bar s. And s is the Laplace transform parameter, and it is a positive real constant. And actually, in preparation for Dr. Kim's viscoelasticity workshop, I spent a lot of time on online trying to learn more about the Laplace transform, trying to kind of get more familiar with it, so I wasn't relearning as I went along. There's a lot of great information out there, folks. This is just scratching the surface, but it's very easy, for example, to find example functions. So the initial time-dependent function, ft, and then the Laplace function on the right. So you can see any sort of function, delta of t, the Laplace transform is 1. If it's just t, it's 1 over s squared. E to the b, negative bt is 1 over s plus b, and then t to the n is s to the n exclamation point divided by n plus 1. Now, it is important to note when we're interconverting between the relaxation modulus and the creep compliance, it is not simply a inverse relationship. And that is because in relaxation, the resulting stress is a function of time. In creep, the resulting strain is a function of time. So because the time dependency is different in these two ideas, you can't just simply take the inverse. But one of the powers of the Laplace transform is you can take the inverse and multiply it by s squared in the Laplace transform space. So if this is where the power of Laplace transform and the correspondence principle comes into play, is you can convert directly between the relaxation modulus and the creep compliance, but it has to be in the Laplace domain. All right, one more key concept that I want to cover. And if you recall back way to the beginning of this recording, this is actually one of my favorite concepts, and that's the time-temperature superposition. So I love working in the lab. One of the reasons I struggle with viscoelastic theory is that once you get beyond the springs and the dashpots, it's hard for me to visualize. It's hard for me to wrap my head around some of these concepts. And that's why I like material testing, because you actually have a physical material and you're doing something to it. Well, In the lab, you have both equipment and testing limitations. So if you have a really, really nice environmental chamber, generally that means you're going from about negative 40 degrees Fahrenheit to about positive 70 degrees Fahrenheit. Not to mention, once you get above 70 degrees Fahrenheit, it's difficult to maintain the integrity of your samples if you're using asphalt mixtures. Again, equipment limitations is loading frequency. This is how quickly do you apply a load to a sample. So generally, our lab equipment can go from 0.01 hertz, and then it can go all the way up to 25 hertz. And I apologize, that should be a capital H, not a small h. But really anything beyond there, you need very, very, very highly specialized equipment. And in fact, if you ever have the chance to go to NC State to visit their lab, which I encourage that you do, they have a Bose load frame which uses speakers and sound in order to get higher frequencies, which is really cool, but we don't have one of those here in Arkansas. So what's the solution to these limitations? Well, if a material is thermorheologically simple, which asphalt materials are, that means there's a similarity between time and temperature, and you can use this similarity on both modulus and compliance. So I mentioned dynamic modulus before, and if you look at AASHTO R62, this is the standard practice for developing dynamic modulus master curves for asphalt mixtures. So basically what you're doing is you're applying an axial load in the configuration on the right, and you're measuring an axial strain. And you are constrained in the lab by temperature and loading frequency. And in fact, this specific piece of equipment, which is in the lab here at the University of Arkansas, it actually only goes down to about negative 12 degrees Fahrenheit. It only goes up to about 60 degrees Fahrenheit. So it's even narrower range than the temperature I listed here. But you go up to the University of Illinois, and the testing chamber they have there, that can actually get down to minus 40 if you need it to. So it just depends on where you are and what capabilities you have. But what is this time temperature superposition? How does it work? Well, if we're constrained by this 0.01 hertz to 25 hertz, and we're constrained by temperature, this is what we do. We run multiple tests at multiple temperatures. So we put our sample in the oven at minus 10 degrees Celsius, excuse me, not in the oven, we put it in the environmental chamber at minus 10 degrees Celsius, and we run the dynamic modulus from 0.01 or 0.1 hertz all the way up to 25 hertz. With that same sample, we heat it up to 21 degrees Celsius, we run it from 0.1 to 25 hertz. With that same sample, we heat it up to T2, 54 degrees Celsius, run it at 0.1 to 25 hertz. So here, our equipment is constrained by 0.1 to 25 hertz, and all we can do is change the temperature, and we change it from negative 10 up to positive 54. And what's happening here is you can see that the colder temperatures, the ones on top, those are a stiffer mixture. And we can measure that stiffness at these three different temperatures from the frequency of 0.1 to 25 hertz. Now what can you do to create a master curve? Well, you take these three sets of data and you simply shift it. So you use a shift factor, which is A sub t, and using that three temperature example, your reference temperature is the middle temperature, A sub t is the temperature shift factor, and then F sub r is the original frequency times A sub t, and you get the reduced frequency. And you can see here, the curves shift. And when you shift those curves, you now have log reduced frequency on the x-axis. You still have the log dynamic modulus on the y-axis, but now on the x-axis, you have log reduced frequency, and your reduced frequencies go from about 1 times 10 to the negative 8 to 1 times 10 to the negative 8 up to 1 times 10 to the positive 8 hertz of log reduced frequency. And so what we did now is we got a much larger range of frequencies. So you can do much faster loads going over, interstate type loads. You can go much slower loads going over, parking lot loads. This really allows us to explore a much wider range of frequencies by simply using time temperature superposition. And this shifted continuous curve is known as a master curve. Now, how do you calculate this master curve? Well, one example is a sigmoidal function. So this is an AASHTO R62, but you can see that you have a dynamic modulus, the log of the dynamic modulus, and that equals various fitting parameters and the reduced frequency. This is just one example. This is in the standard, so this is kind of the default go-to. There are other ways to do it as well. But it's important to note that you have 4 fitting coefficients, and so what you need to do is you need to shift the data, and you can do that either by WLF or the Arrhenius or other various methods. But you can see here the original data, the -10 is on the far right, the +54 is on the far left, and we shifted that data to various reduced frequencies, and then we put a fitting parameter to it. And that's that solid red line, which is the master curve. And you can see the various coefficient values and the standard square error. So you want to minimize that. We usually use Microsoft Excel Solver to minimize that, but it's a very powerful tool in asphalt materials. In addition to these very basic calculations of a master curve, there are various research grade methods as well. Again, that could take 2-3 hours to cover all of those and the ins and outs and the details of each one. So I went over a lot of material. If you are interested in further learning, I do encourage you, if you ever have the chance, to go to Dr. Kim's workshop, the Viscoelastic Continuum Damage Model of Asphalt Mixtures and its Applications. Great 2-day workshop. I learned a ton, took a lot of notes, and it was a very, very good experience. He was also the editor of a book called Modeling of Asphalt Concrete that was put out by ASCE Press. It's a little older, it's in 2009, but it's still got a lot of good foundational information in it. A lot of the material that's covered in that workshop is also in that textbook. Then we have Yusuf Shah and Airy. They put together a very nice literature review of the modeling the linear viscoelastic rheological properties of bituminous binders. That's in Construction and Building Materials back in 2011. Great document, goes into fantastic details. I use that quite a bit. And then there's also a very nice book, Applications of Viscoelasticity by Haji Karimi and Najad. And chapter 3 specifically goes into the models, but the title of the book is Applications of Viscoelasticity, Bituminous Materials, Characterization, and Modeling. And this was put out in 2021. I'm going to sound like a broken record. There's a lot more out there, folks. Lots and lots of information. This is just intended to give you a very broad overview, a big introduction, and I really do apologize if I missed something. If I did miss anything, please email me, afbram@uark.edu. Give me some resources. Once this video hits 1,000 views, I will make a new one because I know there's stuff out there I missed. I probably made some mistakes in this presentation. Please point them out if I did. But I think there's a lot of good information and at least a starting point for you if you're interested in learning about viscoelasticity and asphalt materials. So in closing, we covered the basics. We talked about some analogues and characterization, and then we finished up the behavior. So thank you very much for sticking with me this long. I appreciate it, and I hope you have an absolutely wonderful day.